Okay, so we'll do a very short lecture today because I think most of the stuff you already know. So this is about the characteristic polynomial, eigenvalues, eigenvectors of the linear transformation. So we define the eigenvector to be of this form. T applied to V gives me the eigenvector back with a scalar. So the question is, how does one go about finding the eigenvectors? Well, it turns out that it's easier to first find the eigenvalues. So how do we do that? Well, we have this equation, and that essentially means T minus C of I, where I is the identity matrix, V is equals to 0. So I have a linear operator and I applied it to V to get 0. What does it mean? That means that the vector V, this implies the vector V, is in the kernel of the linear operator T minus Ci. First of all, why should this be a linear operator? Why a linear operator? Well, you can show it. This is not a big deal. This is the sum of two linear operators. This is a linear transformation. So it will be a linear operator. So let's first see, for finite dimensional vector spaces, just a digression, for finite dimensional vector spaces, the following conditions are equivalent. So I can say the kernel finite dimensional vector spaces consider a linear transformation T. Kernel of T is greater than 0, which is also equivalent to saying that image of T is less than 0. Third is that if A is the matrix of the operator with respect to an arbitrary basis, well, then determinant of A is equals to 0. And fourth equivalent condition is 0 is an eigenvector of T, the linear transformation. So you can see that these conditions are indeed equivalent. Well, of course, when the kernel is greater than 0, that means, the image, the image is less than, image of T is not the whole vector space V. So these conditions we already saw from the dimension formula. Now we also know that if the determinant of A is not 0, then a certain AX equals to 0 has only trivial solution if determinant of A is not equals to 0. So for x to be in the kernel and the kernel being greater than 0 means that the determinant has to be 0. And certainly all the vectors in the kernel satisfy this condition that 0 is an eigenvalue, eigenvector. Sorry, this should be eigenvalue of t. By definition, we consider any vector in the kernel to have the eigenvalue 0. Uh, so if these four conditions are met, all of them are equivalent. So if any of these four conditions holds, then we call that such a linear operator is called as a singular, else it is called as non-singular. Now in Artin there is a very interesting example that how these conditions are not equivalent for an infinite dimensional vector space. I would urge you to see that example. It's an interesting example. It has to do with the shift map basically. Anyways, so how do I go about finding the eigenvalues? I have this thing. A was a matrix of the linear transformation. A is the matrix of the linear transformation. A minus IC applied to V is equals to 0. So what's the idea? The idea is that the condition for eigenvectors was t minus c's of I applied to V was equals to 0. And if I had the matrix A, the matrix of the linear transformation, then I got this guy equals to 0. So from here, and with the equivalent condition where we need determinant of A equals to 0, that was a condition for 0 being the eigenvalue, kernel t greater than 0. So this guy is an eigenvector of the linear transformation if this condition holds. This condition holds if the determinant of this matrix is equals to 0. So the value of C for which determinant of A minus C of I is equals to 0, then we will have, for those values, we will have A minus C of I V equals to 0. So that way we can see that we get the value of C for which this particular condition holds, and this gives us a concrete way of calculating eigenvalues. This gives us a concrete way of calculating eigenvalues and eigenvectors. So that is all there is to it. We can consider an example. So consider the matrix 3, 2, 1, 4. A minus C of I gives me 3 minus C, 2, 1, 4 minus C. And determinant of A minus C of I equals to 0 implies C is either 5 or C equals to 2. Okay, so to find the eigenvectors, so again, once again, I hope this condition is clear to you. See, we demanded the kernel of t greater than 0 because we ultimately want to find the kernel of this linear transformation, which was equivalent to the condition, the values of c for which the determinant has to be equals to 0, because this was an equivalent condition out here. So once we have the values of c, we plug those values back to see or we can replace v by the coordinate vector of v and a minus 2 of I x equals to 0. So we get v1 equals to 1 1 and v2 equals to 2 minus 1. So we can consider an arbitrary matrix. So let's consider an arbitrary matrix. I'm sure most of this you guys already know. So this is page 1, 2, 3, 4. Let's consider an arbitrary matrix and I want the values where I have determinant of t of I is equals to 0. Now it doesn't matter, I replace it t by c. I'm using the variable t over here because that's what is in your book. But we need to find the values of t such that this holds, and whether we do it a minus ti or ti minus a, it doesn't matter. So ti minus a is nothing but t minus a11 minus a12. I'm just expanding the matrix a13 minus a1n, something like that. I have here t minus a n n minus a n1, so on and so forth. So the determinant in general is a polynomial. If I calculate the determinant, it's a polynomial. I represented by the symbol, and this is known as a characteristic polynomial, where A is the matrix of T with respect to some bases and the eigenvalues are nothing but the roots of the characteristic polynomial. Eigenvalues are the roots of the characteristic polynomial. So few properties of the characteristic polynomial. The characteristic polynomial does not depend on the choice of bases. Why, you may ask? Well, characteristic polynomial essentially gives us the eigenvalues. Eigenvalues are properties of a linear transformation. It shouldn't depend upon the basis. That's a simple explanation. The other thing is you can explore the determinant. The determinant is nothing but t of I minus a. Now I can change the basis. So the change of basis gives me gives me determinant of, if I change the basis, I have piece of I minus A P inverse. You see P inverse gives me the change of basis, and that is with the property of determinant of three matrices, these guys. So this is determinant of P, determinant of T sub I minus A, and determinant of P inverse. Well, these guys go to 1, so I have the same thing. I have the I have this guy. So uh, change of basis doesn't lead to a change in the characteristic polynomial. Also, you can see when you expand, the characteristic polynomial is of the form of T sub n minus trace of A on the diagonal, T sub n minus 1, some terms, and then I have minus 1 to the power of n. The last coefficient is the determinant of A. You can expand and check. That's fundamentally what the polynomial is. And so you can essentially conclude that this polynomial is unchanged. So the characteristic polynomial trace determinant only depend on, since it's a function of the eigenvalues, on operator T, and is independent of the basis. Okay, so this was a short class. We will meet on Friday. Thank you.